points on the root locus. So what is the angle criterion of the point of the root locus? You take the summation of the angle subtended at the open loop 0 minus the angle subtended at the open loop poles, and they should be equal to what? They should be equal to minus 180 plus minus k 360 degrees. Correct? That means based on this, what we are saying here is we are looking at, so when we talk about angles subtended at the open loop poles and zeros and so on and so forth, we are basically measuring. So from this point, so what we are saying is we basically sum all the angles. This one is given, this definition is already given in your notes, so you don't have to copy it down. So this one is actually at the open loop 0 minus angle summation of all the angle subtended open loop pole, and that should be equal to minus 180 degrees, right? Plus minus 360 degrees times k. So that is basically, that's what they asked for. And of course, the second part is you need to show. You need to show, this will be one of the examples that you can use. Because if you know this is basically part of the root locus, if you pick any point along this part of the root locus, apply your angle criterion, it should add it up to be minus 180 degrees. So if you were to try it, okay, if you were to try it, you can actually see that if we pick this point as a test point, I call it S1. So if you were to measure the 0 to this point, the 2 zeros, so this is the first 0, Z1, this is Z2. So Z1, Z2 contribute what? 0 degree, right? So you get 0. So based on this, what you get here, you got 0 degree plus 0 degree, and then you minus. So now you come to this, this is also equal to 0, because if you measure S1 to this P, okay, so this is P1, P2, and this is P3. So to P3 is actually 0 degree. To P2, 0 degree. To P1, what is the angle to P1? Minus 180 degrees. Alright? And when you sum it up, what is that? That is equal to minus 180 degrees. Basically, is equal to minus 180 degrees plus minus 360K. Alright? And that is why the angle criterion can actually be applied to determine, okay, to determine the root locus on the real axis. First time. Sure or not? How would you all do it if you were to do it? Something like this also, right? Okay? Alright, so this basically, that's what you need to do. Okay? Alright. Okay, second part of it. In the DVD player, the laser which follows the optical track in the DVD is mounted on a mechanism controlled by a servo motor. The dynamics of the servo motor together with the control system can actually be modeled by system with an open loop transfer function. So you are given this open loop transfer function. So in a way, take the hint very seriously, because when you work it out along the way, when they give you the hint, especially polynomial equation, you know that that has to be the solution. So when you try to work it out along the way, you don't get the same thing, you know you're on the wrong track. Okay, so typically higher order polynomial, the Glasgow side will give you what is the solution to this higher order polynomial. So it's very standard. So when you work it out, no matter what, die also try to see how you can actually get it to be the same and check through your answer. Okay, basically that's a check for you to confirm that whether you're on the right track or you're on the wrong track. Okay, so in this question here, you're given this. So they tell you in this equation, your open loop transfer function, you have 1, 0, you have 1 pole, 2 poles, 3 and 4. So all in all, you have 4 poles. Okay, you have 4 poles. So in a way, they work it out. This will be your characteristic equation. I mean, this will be your denominator polynomial. It's a 4th order, and then you have 4 poles and 1, 0. So identify the open loop poles and open loop zeros of the system. So basically, you need to work it out. What is the open loop zero? Your open loop zero will be, right? So 3 marks. This is actually much better. In the past, the arrow paper give you only 1 mark to identify the open loop poles and zero. And I fought very hard to get 2 marks. So because why? You make a mistake, you got nothing. In the arrow paper last time they give you 1 mark to identify the poles and zeros. You make 1 mistake, you 2 correct, 1 mistake, 4 correct, 1 mistake, you got nothing. Because unless you're given half a mark. So if you're not given a half a mark, then that fourth portion is gone. So this one is actually much more generous. So you have your open loop 0. So S is equal to -2, and then your open loop poles. So you need to actually work it out. So S is equal to 0. So that is the first one. -4, second one. And then this one, basically, you need to work it out, right? So this is S plus 2 squared plus 2 squared. So what is this one? Basically your zeta omega n, right? So basically this is what? This is -2 plus minus J2. Am I correct? I'm only guessing, huh? Okay, you have to check, huh? Because this basically will give you what? The bottom here, S plus 2 squared is basically, if you remember from your first semester, your ODE, right? S plus 2 squared, when you do Laplace transform, that basically give you e to the power minus zeta omega nt. So that basically go into your zeta omega n. Zeta omega n basically is a sigma. That's why it's that's why I put it as -2. And then this one is basically your omega n squared. Omega n squared is 4, omega n is 2. Wait, omega d. I think it's omega d, right? That one you better go and check, because or else I give you the wrong one. I'm just hypothetically, I'm going to check. Okay, so this one I put it as check. Okay, because this is, because you know that it's basically minus sigma plus minus j omega d. Okay, alright. So first part, 3 marks. Right? 2 minutes to finish. Draw a root locus for this system. You may calculate any double points or angle of arrival, departure from complex singularity, but may estimate any point of instability. Okay, any point of instability. So this is basically it's a 9 marks problem. So actually they are not so bad. So you have 4 poles and 1 0. So what is the relative order? Relative order is equal to 3. So asymptote. What is the asymptote? Angles of the asymptote. Angles of asymptote plus minus 60 degrees plus minus 180 degrees. Alright? Okay, if you cannot remember that, use the formula. Okay, I've already sent you what you're going to receive together with your exam paper, the data sheet. Everything is actually inside there. Okay, so you have this. So what you need to know is you need to find out the intersecting point x. So what is the intersecting point? Intersecting point here is going to be 4 minus 1. So you will be summation of 0. Summation of 0 is going to be the summation of pole minus the summation of 0. Summation of pole, as we mentioned, you take only the real portion. Right? You only take the real portion. So you got 0 plus minus 4 plus minus 2 plus minus 2 minus 2. Correct? Am I correct or wrong? Okay, so when you work it out, this will cancel this. So you have minus 6 divided by 3 is equal to minus 2. Okay, so for this case here, you also need to determine, right? So as what we mentioned, you have, this is your sigma, this is your real, this is your j omega. Okay, j omega. So in this case here, you have a pole at the origin, you have a pole at minus 4, you have a pole at minus 2, plus minus J2, okay, based on my rough calculation. So this is plus J2, this is minus J2, and then you have a 0 at minus 2. Okay, so this is a case where you need to calculate the angle departure. We did mention that we will not dwell too much into the angle departure, so you can refer back and then try to make use of what we have given to you, and then you try to work it out and calculate. But typically, you know that this will be part of the root locus, this will be part of the root locus also, right? Okay, so this portion of it will be root locus, this portion of it will be root locus. The only thing what you need to do is you need to calculate the angle of departure, because why? Because you have a pair of complex conjugate poles. So this pair of complex conjugate poles, it depends on how is that going to be basically departing, right? Because when you work it out, you work out what is the real axis intercept. Your x is actually at minus 2. So I mean, this is not correct, huh? This is 45 degrees, so 60 degrees is like this. So likely this will be like this will be like this. Okay, alright, so this one is wrong, because this is only 45 degrees. So this one will be more likely. So roughly, this is what it's going to be like, and you do not have any double point right now. Because the question basically asks, draw the root locus of this system, you must calculate any double points or angle of arrival departure from complex singularity, but may estimate any point of instability. So the point of instability, you can actually just estimate. So what happened here is, as I mentioned, bring your protractor. Still remember what is your protractor, right? You can actually measure the angle, you draw the line. Hey, because a lot of you after O level, no need to really throw away, give it away. Your what do you call it? Your mathematical set. Right? I thought in poly you get more kilat one, right? The set square and all that. Yeah. But you need your protractor to work out the angle. Right? Because in this case here, it's a straightforward 60 degrees. Right? And typically in this question, however, they didn't ask you, but in a lot of the paper, those I sent it to you, they did ask you to use 1 unit equal to 1 cm or 1 unit equal to 2 cm and all that for your graph. Okay, so remember, where do you find the graph paper? Center of the booklet. Center of the booklet you need to actually use to actually do all this. Okay, so I guess that's about it for 9 months. Okay, so one thing is we didn't really say too much. Okay, can you all confirm with me? When you read through the notes that I sent it to you, was there anything mentioned about dominant complex poles? No. Sure. Because I see it almost every paper they ask. No, because I didn't see it, so but I'm not too sure, because I know you will scrutinize word by word. I just scanned through, I didn't see anything. Dominant complex pole, because I didn't cover with y'all. Because sure. You want to learn dominant complex pole? Okay, basically the concept is very simple. Okay, as far as concept is concerned, the concept is very simple in the sense that we are looking at a system. Okay, typically you can actually work with unstable system. You can also work with stable system. So, say for example, I have a system that I have a pole here. That's closed loop. I'm not talking about. So when you talk about your dominant closed loop, when you talk about your dominant poles, we are referring to your closed loop system, right? Closed loop system. Okay. And what happened here is you have poles here. You get poles here all over the place, 0. You can have all over the place 0 poles and all that, and then you have poles here. Okay, so maybe I changed it. This is here. This is something like your Fugoi mode. You learned about Fugoi mode right now. Have you all learned Fugoi? Short period and Fugoi mode. It's lucky, not it. Your longitudinal motion, right? The fourth order, the state space, and you actually, when you're looking at your longitudinal axis, you basically have a Fugoi, you have a short period. So this is basically like your Fugoi. This is like your short period. Okay, so what happened here is, in this case here, so you have all kinds of combination and all that. So the dominant pole is very simple. All you need to do is, you are looking at any of the poles that are closest to your j omega axis. So it can be something that is on the right half plane, right? Because if I have to put something at this point here, if I put a pole here, then of course this pole is actually closest. Right? If I put this pole at this point here, this pole will be closest to the j omega axis. Or else, what happens is, among all this, right, this pair of poles will be the closest to your j omega axis. Right? This pair of complex conjugate poles will be the closest to your j omega axis. And as a result, it has what we call a dominant effect. That means what it does is it dominates your response. If you do a step response, your system primarily will show up behaving like a system with just a pair of complex conjugate poles. And typically, what happens here is, the rule of thumb basically is about 5 to 10 times. Okay? So what you do is you measure this is your zeta omega n, right? This is the real part of it. So all you need to do is to measure the ratio of the distance. You measure all the distance. Okay, you measure all this distance that you can. If they are basically 5 to 10 times, what you're saying is, if you want to do a lower order approximation, you can actually ignore them. Alright, because why? Because if the distance are between 5 to 10 times the real part of this complex conjugate pole, basically you say that you can actually ignore them. You can actually ignore them. Because why? Because if you remember why we call this a dominant pole, because why? Because when the pole is actually very close to your j omega axis, your zeta omega n is a very small value. So you have e to the power of minus zeta omega nt. So that is a decaying exponential term. So if that term is actually very small, 0.05, compared to another term that is actually far out here, minus 100t, what happened? 1 second, that one disappeared already, the transient, no more, steady state, decaying to 0. Whereas this guy, 0.05, it takes a long time for the transient to decay to steady state. So as a result, the effect is actually much longer lasting. And that is why we call it the dominant pole, in a sense that it actually has a dominating effect. Okay, so one thing is a dominating effect. That means in this set of poles and zeros, with this, the complex conjugate pole is a dominant pole, meaning if I have to take a look at the step response, okay, if the rest are far away, the behavior of the step response behaving primarily like I just have a pair of complex conjugate pole, right? It will behave like, if you take a look at the step response, it behaves like you only have a pair of complex conjugate pole. The rest of the pole not present. And that is why we say that you can actually use what we call a lower order approximation. When you do controller design next time, you will see that sometimes your lower order approximation is a very good technique to use. Because why? Because when you add your actuators, your sensors and all this and that, a very simple second order system, when you add all this thing out, it becomes a 6-7 order. How to design a controller. So what happened is, first cut, you do a lower order approximation. So I try to approximate my system to be a lower order system, then I design a controller. So that is also one approach that we will use, right? For analysis, this basically will represent your dominant complex pole. Dominant complex pole, as I explained to you guys, the reason being because the time constant is very long. It takes a very long time. If the closer you are to the j omega axis, the longer it will take for your transient to decay to 0. So as a result, it dominates during your transient phase. Okay, it will dominate your transient during your transient phase. poles that are actually very far out into the left-hand plane has very minimum effect at all, right? Because why? Because if this is e to the power of minus 100t, t is equal to 1 second is e to the power of minus 100. Maybe already decayed to 0, very small value. Whereas if this is e to the power of minus 0.05, it takes a long time. Okay, so that is why we call that a dominant complex pole. Okay, so primarily that's what they ask you to identify, right? You need to actually, if you need to work it out, you need to identify. So from the diagram, determine the value of K that will result in the dominant complex poles having a damping factor of 0.4. So if we come back to this, we know that the dominant complex pole is going to be coming from this root locus here. Because the root locus, what does the root locus give you? The root locus here primarily gives you the closed loop pole. So as what we did during our lab, so you need to work it out because the damping is 0.4. So you have cosine theta is equal to 0.4. Alright, is equal to your zeta. So theta is going to be equal to your arc cosine 0.4, and you basically have to draw a line. So in this case here, you need to draw something fairly accurate. And find the intersecting point. From the intersecting point, this will be your closed loop dominant complex conjugate poles that will give you a damping of 0.4. Okay, that will give you a damping of 0.4 because this is zeta is equal to 0.4. And what happened here is you need to find the value of K. So how do you find the value of K? Of course, you need to go back and use your calibration equation. Right? So first you find out the angle. You find out the angle already, then you use your calibration. Which one is your calibration equation? Can you remember what is your calibration equation? K is equal to pi. We don't even have any holidays and you erase everything. Then after the holidays come back, your 3-week Easter break come back, everything delete star dot star. Calibration equation. What is your calibration equation? K is equal to pi of what? Pi your distance to open loop poles from dominant complex pole location, right? Okay, distance to open loop poles from dominant complex pole divided by pi of distance to open loop 0. Okay, from dominant complex pole. Okay, guys, this is something that they will ask you. Okay, your new examiner will like to ask you things like that. What is your calibration equations and all that? State what is a calibration equation. So now you're gonna have to memorize. Okay, you cannot just remember how to solve, how to work it out. Because if you don't memorize the wording, so the wording try to be as close as possible. You don't have to match it 100%, but at least, you know, I mean, when I read it, I can tell them, hey, you got it correct, you got the idea correct, and all this and that. Okay. All right. Okay. So you find out. So you need to find out this pole, and then from there you plug it into this calibration equation. You can actually calculate your K value. Alright, okay? And any questions so far? Any questions? Okay, yeah? Alright. Take a look at the next one. Okay, that's what I mentioned to you guys. This is how they would like to test you. State the definitions of the gate margin and phase margin. Okay, for 2 marks. Not a lot, but it's a waste if you throw it away. So you can imagine that you need to at least explain halfway decent. What is the gate margin? What is the phase margin? Right? Because gate margin 1 mark, phase margin 1 mark. Alright, gain margin 1 mark, phase margin 1 mark. So you need to be able to explain what is the gain margin, right? Because you know that the gain margin primarily is the factor by which the gain would have to be increased to just cause instability. Right? So that is your gain margin. Your phase margin is basically a phase lag that would have been, if you can add it onto your system, a phase lag that you can actually add it onto the system, to the phase, to cause instability. And you can actually use a diagram. If you are not very good in writing, you can actually use a diagram to illustrate. So how do you determine your gain margin? You must cross a minus 180 degree phase curve to obtain your gain margin, right? You project it backward. And the other one is basically you work it out for crossing your 0 dB line. Crossing the 0 dB line, then you work backward to find out from minus 180 degree phase to the phase curve. That will give you your phase margin. So that was what we discussed last time, right? Last time we actually talked about this. A very rough sketch. So this is a 0 dB, and then this is your phase. So this one is minus 90, this is 0, minus 180. So you have things like this. Okay. So this will be good enough. Okay, so this is your phase crossover frequency. You measure it out. So this one is your gain margin, right? This is your gain margin. And then from here, you project it down. Your gain crossover frequency at 0 dB line, so this will give you your phase margin. Okay? Alright, so this is just a very rough sketch. Okay? Alright? Okay? Any question to this? I think this is straightforward, right? So if you cannot write it nicely in words, so I'm not so mean. I will not deduct you if you are spelling error and all this and that. But at least I read it, I understand what you're saying. Okay. If you don't think you want to explain in words, well, you draw a diagram. So it's okay. Right? Because it's only 2 marks. One gain margin, 1 mark, one phase margin, 1 mark. If you explain it wrongly and that's it. Okay, it's a waste. But if you have a lot of marks to spare, then it's okay, don't do it. Right? You don't think it's worthwhile for your effort to write it now? Fine, it's okay. But if you think that you need the 2 marks to get an A1, then of course, by all means. Okay? Alright, the next one is basically this one, as I mentioned, it shows up in almost every paper. I'm not too sure whether this one will also show up this time now. Okay? State the Laplace transform of a delay of t seconds and state what effect it would have on the gain and phase margin. Okay, so a lot of time, let me see, another paper basically they just say, I've seen it. See, this one was a main paper 2015 main. So again, state the Laplace transform of a delay of t seconds and hence determine the magnitude and phase of the frequency response of a delay of t seconds. Okay, so I would think that it's worthwhile that you try to at least you understand, and then if you can, you memorize how to actually try to work out what is the Laplace transform of a delay of t seconds and state what effects it will have. So what is a delay of t seconds in Laplace transform? Your delay, as we mentioned, any time delay is equivalent to what? Multiplied by your exponential term, e to the power of minus st. Correct? This one was last semester. All returned already last semester. AN2S. So those who score A1 for AN2S will be able to remember, right? In fact, 90% of you all passed AN2S, so that should not be something that you can come and tell me that I cannot remember. You better remember, or else I'm not forget. Okay, so basically, this is your power of st. And what happened here is, in a way, we know that they ask you, so this question is slightly different. This question basically asks you the effect have on your gain and phase margin. Okay, so in a way, delay, this is your Laplace transform of your delay. Your delay will always lower your gain margin and also lower your phase margin. Alright, your delay will always lower your gain margin, will also lower your phase margin. So the other type of the question that they basically ask you about your Laplace transform and how to actually work it out to link the delay to your frequency response and so on. Because if you remember, in the delay, Laplace transform is e to the power minus st. What is your s? In your frequency response, s is equal to j omega. Okay, so in this way, what happens now in your frequency response, your delay will be equal to e to the power minus j omega tau, or omega t. Okay, so in this case here, what will happen here is in the frequency domain, if you have e to the power minus j omega t, what will be the magnitude of this exponential term? What is the magnitude? The magnitude will be equal to, what is the magnitude? Magnitude equal to what? Magnitude will be equal to 1. Okay, and what is the phase? Phase is basically, if you still remember, because if you remember that is an Euler form, right? So your phase is going to be equal to minus omega t radian. Okay, this minus omega t, if you know what is the phase, right, for this, the delay, and you can actually work it out because a lot of questions basically ask you based on that. Okay, so you have your phase, magnitude you know is going to be equal to 1, but the phase is going to be equal to minus omega t radian. Okay, we'll see which question basically will face it. Alright, so some of these things that you need to basically take note. Okay, so in this case, so you have 4 marks already. So you still, so assuming that you do 2 problems, right? So what kind of problems are you more comfortable? Dynamics or control? Why don't you all do more dynamics? So I don't have to mark so much. Okay, I think dynamics is also alright. Okay, but the only thing, alright, that's why I say this is not a very good yardstick because this paper, if you can do this paper is actually much tougher than what you're going to be seeing. Okay, it's actually much, you need to do a lot more. Yours, you actually don't have to do that much. Okay, you don't have to do that much. Level of difficulty can be the same, but you just don't have to do that much of a calculation. So this one, they ask you to plot this, plot that, do all kinds of things. In your paper, you might be asked to plot, but not as tedious as what you need to do because a lot of all this we didn't actually have a good practice of it, right? I mean, they ask you to draw an accurate Nyquist plot of this system for a value of k is equal to 1. Okay? Use a scale of 10 centimeter equal to 1 unit. I think it's 10 mm, cannot be 10 centimeter. 10 centimeter is quite a lot. I think it's a 10 mm. 10 mm is actually equal to 1 unit and so on. So that's what they ask you to do. And you have this, okay, so this, let me see. Doesn't get the correct paper, so this one is obvious. Okay, so in a way, in this question here, so they ask you to draw Nyquist plot, basically your polar locus. Alright, for 9 marks, you need to draw this polar locus and all this and that. Some paper, if you look at it, they do suggest what kind of number that you need to use to calculate. So primarily, in this case here, you need to basically, because you're asked to do the polar locus for this. So a few things that you need, of course, to try to identify will be your corner frequency. Okay, so first thing, what will be your corner frequency? You have two corner frequency. One is basically omega is equal to 2, the other one is omega is equal to 8. Right? You have two corner frequency. Right? So you have two corner frequency, 2 and 8. Then of course, based on the transfer function given here, you actually have an integrator. Integrator basically is your j omega is equal to, I mean, you have a pole at the origin. So this is a pole at the origin translated into just a j omega. So this is an integrator. So in a way, you need to do some calculation. Alright, you need to do some calculation. So in the lecture, we did mention, alright, we did mention that you need to try to find out what happened when frequency is actually very small, what happened when frequency is very large, and you need to find out the magnitude. Okay, so when frequency is very small, what will be the magnitude? What will be the magnitude when frequency is very small? It's only two numbers, three numbers at most. 0, 1, infinity. Which one? 0. Right? This is a system with 3 poles. You have one pole at the origin, basically it's an integrator. Okay? So when you try to find out what will be the magnitude when frequency becomes very small. Very high, right? I told you, right? It's either 0, constant, 0, 1, or infinity. So basically, your magnitude will be basically infinite. Okay? What about your angle? Your phase angle. Before we go into Easter break, maybe we cannot. What is the phase angle in this case here? Phase angle. What's the phase angle? You have an integrator. So what is the phase angle when frequency is very small? 0. You have an integrator. I already told you. How much angle does the integrator contribute? Negative 90. Yeah, I see he's smart, so he knows. Just trying not to let other people know that he's smart. I'm just joking, sorry. Okay, so these are the things, because you know why? Because we didn't really go through all this. So you need to basically have something to guide you. So as what we went through during lecture, we did mention that you need to try to identify. Okay, so you need to identify a few things, because this is what, 9 marks. It's a lot, 9 marks. So what happened here is then when frequency becomes very large, what will happen? What will be the magnitude? Magnitude will be 0. Okay? And then the angle. Angle, basically, we say that high frequency phase angle will be approaching your relative order multiplied by minus 90. Right? Because we are working with a system with more poles than 0. So you take the relative order, you multiply by minus 90. In this case here, you have 3 poles, right? So it's minus 270 degrees. Then of course you need to basically write down based on this, because you're given that k is equal to 1. So your gj omega is equal to 4 divided by j omega. Then you have your 1 plus j omega divided by 2. And then you have 1 plus j omega divided by 8. And from this expression here, how do you actually work out the magnitude? So the magnitude is actually we discussed in last semester your complex number. So the magnitude, this will be what? This will be omega, this will be square root of 1 plus omega divided by 2 squared, and then multiplied by 1 plus omega divided by 8 squared. Okay, and that is why I said if you're asked to do all this, it's very time consuming. Okay, and that is why I said if you can, this paper you take it and you practice it, because to plot the polar locus you can use MATLAB. So, but you still need to actually try to do it on your own. Okay, you still need to try to do it on your own. Because with this, you can actually, by looking at this, I mean, if you're familiar, you can roughly sketch it out. Might not be that accurate, but if I have to sketch it, I roughly know. Because I started off at minus 90, magnitude is very large. So this is the minus 90 line. So your curve basically will come something like this. Right, this is minus 90. So it depends. Well, this is not a very good representation, right? So sometimes what people do is they put this to be very close here. Okay, but this one, because what happened here is, because if you were to expand it, right, you extend it long, to very small, large value, right? Basically, you know that when you draw, angle is basically drawn. So actually, you need to actually tuck it very close to minus 90. Because when frequency is 0, is minus 90. And after the moment you cross your j omega is equal to 2 radian per second, you already start to increase. So in a way, you will start to increase to, you know, this angle, this angle, this angle. So you can actually see that eventually it becomes minus 270, because this is minus 270. So when frequency gets very large, magnitude is equal to 0, angle is actually minus 270, and that is how we draw it. The only thing I do not know is where is the minus 1 point. Okay, the minus 1 point is here, I'm okay. If the minus 1 point is inside, that's what we discussed about your stability for your Nyquist polar locus. You might have instability problem. Okay, so if minus 1 point is here, that is good. Because why? You don't have encirclement of your minus 1 point. You are actually outside. Something like this, I mean, if I have to look at all this, I will sketch it. But for your guys, I think you need to basically try to find out. So you need to actually find out. So from this equation, your angle, and then from your magnitude, you can also work out your phase. So your angle is going to be, okay, let me take out this piece. Okay, so from this, you can also work out what is your angle. Okay, your angle is going to be minus 90 minus arctangent of omega divided by 2 minus arctangent of omega divided by 8. Okay, so you have these two equations that you can actually work on. So in a way, you need to find out what is the frequency. So you have a magnitude, and then you have an angle. Okay, so here maybe you start from 0, and then you start from 0.5, 1, 2, 4, 8, 12, 8, 16, 20, 50, and infinity. So you can see that how many points you need to calculate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 2, 20 points. And that's why it's 9 marks. And then plus you're sketching it out. So that is why I always say, try to practice when you have a lot of time. Right? When you have a lot of time at home, try to practice. Don't do this the first time in the exam, please. If you're going to do this the first time in the exam, don't bother to do it. You're sure to make mistakes. Okay, so you need to practice, because if you practice a few times, you roughly get the catch of it, get the hang of it, you know the technique and all this and that, so you need to know roughly, because we already have this to guide us. Okay, the thing that we are saying that, why do we need this? Okay, why do I actually ask you to work out this? Because this is actually to guide you. This is to guide you that when you plot it out, when you do the calculation, if you make any mistake, roughly you know. It cannot be, you cannot go wrong. If you have this to guide you. So if you're going to calculate your angle become minus 70, you know it's wrong one. In between here, if you're going to be, your frequency is going to be starting from 0 to infinity, it cannot be less than, it cannot be greater than minus 90 and all this and that. And then the maximum you're going to go minus 275. Okay, so that is why this is actually useful. If you can do this, at least the rest wrong, you still get some marks. Okay, I'll see how much I can push you. Alright, but roughly you must have something to guide you so that you work within that framework. So when you calculate, because if you see that you do have to calculate a lot, and that is why I know. And that is why in the past, no one will do frequency domain analysis problem. Okay, since 2012, 2013, 14, so 15, you're the fourth batch. Huh? I think the first batch, maybe 2 guys did it. Last year, I think 1. For two exams, 1 attempted that question. And then 1 year, 0. No one actually attempted the question. Because you need to calculate many points. And knowing your low practice, I can tell you practice and practice and practice, but you have to practice if you really want to attempt. But what I'm saying is, if you are AE, you might be able to get away, but if you're AS student, you will never get away because next year you have another aerospace control. I'm not too sure what they cover inside. They might bring this one out and then test you. So it's good that you know. Okay, because next year your aerospace control is also another 20 credits. So AS student, they really like you to learn control, so you have 20 credits here, next year you have another 20 credits. Okay, so you have to practice. If you don't practice, it's going to be difficult. So the last portion of it, the next portion of it, okay, so you can actually see that once you can plot this, the rest are they will kind of give it to you. Because they say from your plot, estimate the phase margin and show this angle on your plot. Okay, so you need to be able to remember how do you actually work out your phase margin, right? I mean, if you still remember how to work out your phase margin. So if you have the polar locus, can we work out the phase margin? Right? I mean, if that is a polar locus, so if this is actually correct, okay, your phase margin, basically, you need to find out the unit circle, right? Okay, you need to find out the unit circle. This will be your phase angle, and then this will be your phase margin, right? Am I correct? Okay, you better check. So this, this will be basically your phase angle. From here is your phase angle. You need to determine this frequency. Okay, so what happened here is you need to basically, you need to do 2 things. So in this case here, what you can actually try to estimate. So sometimes you might be able to estimate, but sometimes you might not be able to estimate for your calculation is you need to basically try to work out in your magnitude, this will be equal to 1. At this point here, the magnitude is equal to 1. Correct? From here, if you can set, so that's a problem. If you can set your omega, the magnitude, at the phase crossover, to calculate your phase margin, you need your gain crossover frequency at the gain crossover frequency, the magnitude is equal to 1. So you need to make use of this equation. Okay, you need to make use of this equation to try to work out what will be your omega. And you substitute your omega value into your angle equation. You work out what is the phase, and then you take that, your phase minus 180 degrees, then you can actually work out your phase margin. Okay, so in a way, if you can draw this as accurate as possible, you can actually use your protractor to try to measure this angle, because it's only an estimate. And that is why I asked you to bring your protractor. So if you don't have one set, borrow from your brothers or sisters. Okay, those who are still in the school system. Primary school also they have a mathematical set. So all you need is a protractor. The protractor basically will help you to measure the angle for the phase margin. And then you have your gain margin also. Gain margin, they ask you to calculate the gain margin of the system. Calculate the gain margin of this system. So gain margin of this system, primarily your phase angle is going to be minus 180 degrees. So what you can do is you go back to this phase equation, you set this equal to minus 180. You try to find out what is the frequency, right? Set this is equal to minus 180, and you try to find out the frequency, and then from the frequency, you try to work out. Okay, you try to work out what will be your omega, and then from the omega, you can actually try to determine. But in a way, what happened here is because this is actually asked you to estimate, right? So what happened here is you need to measure. You can also measure this intersection point, right? So if this is equal to, in our case here, what do we use? We use this to be the point from the origin to the point that intersecting the minus 180 degree phase. This is your lambda, right? That's lambda is like this. Is that what they use, lambda? Okay, so if you use that to be, if they use that to be the gain value, so what happened here is this distance is your gain margin. Alright? That's how much gain you can actually increase to cause the system to become unstable. Okay? Alright? Any question? Any questions so far? Anything that you want to clarify and all this and that? Clear cut. Understood. No doubts, no query at all. Have you looked at the question and tried to do it? Honestly. How many of you have actually taken a look at the question paper at least? Or at least you print it out? Print it out and that's it. And then found it already. Don't found it, huh? Print it out. You have one holiday already, Friday. Right? You can start trying to do this. I know we have other papers and all this and that, so yeah. Okay, so in a way you can actually see that they are quite kind to you, though they only give you 1 mark. What value of gain K will make the system unstable? Gain margin. Because you already worked it out, calculate the gain margin of the system. So this 1 mark basically is giveaway. So in a way, if you get it, if you get a gain margin, this 1 mark is giveaway. If you don't get the gain margin, then this 1 mark is taken away. Okay? Right? Because they ask you what value of gain K will make the system unstable. And that's what we mentioned before. If you work out the gain margin, okay, if you work out the gain margin is equal to 1, or if you work out the gain margin is equal to 2, then what value of gain K will make the system unstable? K is equal to 2 will make the system unstable. Okay, because what? Because initially your K is set at 1. So what happened here, any gain margin comes in, you multiply it by K, actually absorbed by the K value. Okay, all right. Okay, this is also one. Okay, next, the last question. This is also one that you see it over and over again. State the Routh-Hurwitz stability criterion as it applies to first, second, and third order system. Okay, so how do you actually do this? How do you actually? It's quite straightforward. 4 marks given to you, but it can be 4 marks getting back from you. Okay, so you know that for this problem, your first order, second order, and third order system. So what is your first order characteristic equation? So what you need to work it out is you need your characteristic equation. First order system is A1S plus A0 equal to 0. Okay, so in this case here, what happened is, so this is your first order system. Your second order system is A2S squared plus A1S plus A0 is equal to 0. And then of course, the last one is going to be A3S cubed plus A2S squared plus A1S plus A0 is equal to 0. Okay, so first and second order, straightforward, right now. For first and second order system, primarily any gain. No problem, right? Because it's a characteristic. This is a characteristic equation. That's what we mentioned. In your root locus, when you have one pole, what is the root locus? What is the asymptote? When you have one pole, what is the asymptote of your root locus? Caleb. When you have one pole, yeah, 180 degrees, right? Yeah. Correct? 180 degrees? 180 degrees. So as a result, in your root locus, if the asymptote is, the angle of asymptote is 180 degrees, basically it moves into the left half plane, always stable. And then your second order system, A2S squared plus A1S plus A0 equal to 0, characteristic for your second order system. Second order system, your asymptote is plus minus 90 degrees. Right, straight away, primarily, you'll just go up and down. Right, plus minus 90 degrees, you're not going to move into the right half plane. Okay, so what will be the requirement for this two? The basic requirement for this two will be the pole, the coefficient must have same sign, correct? The coefficient A1, A0, A2, A1, A0, they must have the same sign. Agreed? Why? Why? Why they all must have the same sign? Stability, yes. Because if you have A1S plus A0, A0 is a negative sign, so you ended up, okay, if A0 is a negative sign, so you have A, so I put a value in, so I got 5S minus 2 is equal to 0. Okay, so what happens now, if you have S is equal to 2 divided by 5, this will place the pole on the right half plane. Okay? Your coefficient to have the same sign primarily is to ensure that your pole at least stay in the left half plane for first and second order system. And that is why, if you remember, long time ago when we talk about your second order system, I told you, right? When you do your Laplace transform, typically system, if they are stable to begin with, you check your coefficient. When you do your modeling, you learn from Dr. Alfred, you do the modeling and all this and that. If you're working with second order system, as long as the second order system, you more or less you know whether you're on the right track or not. Because when in your equation of motion, coefficient must all have the same sign. Because the moment the coefficient have opposite sign or different sign, you know that the system can be unstable. So it's the same thing in your quadratic equation, right? The second one, A2S squared plus A1S plus A0. If they are all having the same sign, you are ensured that the pole will be in the left half plane. So stability is already there. Except that when you come to your third order system, right? Your third order system here is A3S³ plus A2S squared plus A1S plus A0 is equal to 0. So what we need to do is, as we talk about your roof stability criterion, we need A0, A1, A2 and A3, they are all greater than 0. I mean, to be consistent. So your AI has to be greater than 0 or less than 0. It depends. Then of course the next thing that we need to do is we need to form the roof array. Okay, so you have your A3, A2, A1, A0. So this will be your A0, alright? I mean, as we mentioned, when you're familiar, and then so what happened here is basically this is a pivot minus 1 divided by A2. So this will be A3, A0 minus A1, A2. Correct? And then we want this to be greater than 0. So taking into consideration of the minus sign, we have 1 over A2, and this is basically A1, A2. Alright? Minus A3, A0. Okay? So what happens now is they have to be greater than 0. Okay? If they have to be greater than 0, this has to be positive also. So A1, A2 has to be greater minus A3, A0 has to be greater than 0, implying that A1, A2 has to be greater than A3, A0. Correct? Okay, so this basically will form the condition for your third order system. So when they ask you to, in this case here, they ask you state the roof array stability criteria as it applies to first, second, and third order system. So first, second, straightforward, coefficient all of the same sign, no problem. Third order system, coefficient of the same sign, that is only your sufficient condition and necessary condition. Then you still have your sufficient condition from the roof array. Your sufficient condition primarily will require you that your A1, A2 has to be greater than A0, A3. Okay, so that will be your sufficient condition in addition to your necessary condition. Okay, so as I mentioned, this question come out many times. Okay, I'm not too sure whether it will come out for you, but it's better to be prepared because it's 4 marks like this, and do like this only 4 marks. You don't really do much. If you can remember that, and all this is you don't really have to memorize them because on the spot you can actually derive. Okay, on the spot you can actually derive. So you don't even have to remember. So you roughly only have to remember is how to actually write down your characteristic equation. On the spot you can derive. So on the spot you derive, then you just explain. Coefficient has all to be the same sign, and this is a condition, and that's it. Okay, alright. Okay, then the second part of it, this one I'll leave it to you. Determine the range K for which the system with the given characteristic equation are stable. In the case of part 3, determine the stability of the system as it does not depend on K. Okay, so I'll leave it to you to work it out, right? Because they already give you your characteristic equation. So all you need to do is you need to use a roof array to try to work it out whether the system is going to be stable or unstable. Okay, alright, the last one, part C. Your closed loop systems are given by this, the 3 closed loop systems are given by this transfer function. Closed loop transfer function, G1S, G2S, and G3S. G2S and G3S are all second order systems. G1S second order, but you have a 0. Okay, so what happened here, by considering the position of the dominant pole and justifying your answer, rank the system in order of speed of response, fastest to slowest, percentage overshoot of step response, smallest to greatest. Okay, so in this case here, what must you do? You must basically try to work out. So what do we actually need to work it out? You need to work out the poles. So you have your G1 is equal to S plus 3, S plus 2, S plus 4. G2S is equal to what? You have your S squared plus 10S plus 29. So this is what? Okay, correct? S plus 5 squared plus 2 squared. Right? 5 squared is 25, plus 4 is 29. The last one, G3, is equal to 1 over S squared plus 2S, so it's S plus 1. Right? S plus 1 squared, so it's 1, so it's 25 plus 5 squared. So in this case here, so what happened here is all you need to do is you have, if you were to come back to this, so for first one is minus 2 minus 4. Okay. Second one is so this is the second one is minus zeta omega n, so basically is here. Right? Minus 5. So it's minus 5 plus 2, so it's minus 5. So this is G2. So this is your G1. And then the last one is minus 1. So minus 1 plus 5, so it's basically here. So this is J5. This is minus J5. Okay, so from this, they ask you to basically try to find out. Okay, so you have from this, so this is your first system G1, this is G2, this is your G3. Okay, dominant pole, this is minus 2 because you have two poles, right? You pick the one closest to the j omega axis, so you pick this. So that's the dominant pole for your G1. For your G2 is actually this is minus 5, so this is actually minus 5. Your G3 is actually minus 1. Okay, so now if I have to ask you which one will be the fastest system? Okay, so who wants to volunteer? Alex, yeah, Alex Ng. There's an Alex Ng, there's an Alex Lim, is it? Alex is always a smart one. That's why smart Alex. Okay, what happened to the attendance? I got your this. But this one is only AE. Yeah, that's Alex Ng Man Heng. Alex Ng. Okay, so which one will be the fastest? Where's Alex Ng? Where? Alex is. Which one will be the fastest? And why? You have G1, G2, and G3. Okay, Alex said G2 is the fastest in terms of the step response. Okay, why? Furthest away from the j omega axis. The rest of you all agree or disagree? The rest, I hear only one yes. The rest? Sure, supporting him, huh? So brothers, Rob also support, never mind. Brothers, okay, he's correct. So what is the second one? Second one will be your G1, right? And then the slowest, and slowest, as I explained to you why dominant poles always the slowest, because closest to the j omega axis, the transient basically very long time to decay. So dominant effect. So G3 will be the slowest response. Okay, G3 will be the slowest response. And then the next question they ask, so these are the things that you need to prepare. Percentage overshoot of your step response from smallest to the smallest to the greatest. Okay, smallest to the greatest in terms of percentage overshoot of step response. Mark. In terms of step response, which one will have the smallest overshoot and which one will have the greatest overshoot? Don't be shy. You can see it and you can tell us already. What? Question basically percentage overshoot of step response from these three dominant poles for system G1, G2, and G3 from the smallest to greatest. Which one is the smallest overshoot? G1? Which system will give you the smallest overshoot? G1 will give you smallest overshoot. This one will give you smaller overshoot. Is that the answer? Okay. Agreed? G1 will give you smallest overshoot. Agreed? G1 will give smallest overshoot. G1 will give the rest of your. Yes. Unfortunately, I cannot remember your name. This guy, Cyril. Yes. So, I think Mark said G1 is the smallest overshoot. You agree or disagree? How do you justify that to be the smallest overshoot? Smallest overshoot. Mark said G1 give you the smallest overshoot. So who wants to help Mark? He said G1 has the smallest overshoot. Any ladies want to help Mark? I only know it is Hui Feng, is that it? Hui Feng? Or it's a guy? Okay, I'll pick the one, cannot go wrong one, Karin, are you here? Kyling, right? Yes. Okay, your friend already said G1 the least overshoot. The question here is why G1 has the least overshoot? I just want you all to share the knowledge so that everyone learns together. Yes. You don't want to share with them. Anyone wants to help? Hey, where's the Mr. Macho? I forgot his name. Yes. Well, now you even started Yes, why is G1 the least overshoot? Okay, listen, answer is because the poles are actually on the real axis. So when you have poles on the real axis, that's what you remember. They are either over damped or critically damped, right? So because at best, critically damped, that is where you have the double point. If you remember, when we talk about double point, repeated poles for second order system, basically critically damped. Damping is equal to 1. Other than that, on the real axis, damping greater than, damping equal to 1 when you have double point. Elsewhere, unequal roots, damping greater than 1, you will have no overshoot. So that is why G1 will give you the least overshoot. Then of course, from here, you can tell by measuring the damping, right, between your G2 and your G3, and you can see that G3 actually has a very light damping, right? G3 has a very light damping, so will give you the maximum overshoot. Correct? This point here, because this is actually -1 plus minus J5. So when you work out the angle, you can actually work it out. The cosine angle is actually very small. Cosine angle is very small, meaning the damping is also very small. Okay? Alright? Okay now. Okay. So we take 5 minutes break, then we'll come back and look at the main paper.